Okay, so let's continue with the surface parameterization, and let's find a parameterization of the cone z equals x squared y squared with the root, and it says z is between 0 and 5. So what is my surface in this example? So this equation, it is exactly this cone. It's the upward cone of height 5. So here on the z-axis we have 5, and this is my cone. So it is, again, it is composed of circles, because at each, if you look at like a side, if you look for fixed z, what is the equation? It becomes z equals square root of x squared y squared, which is basically x squared plus y squared equals z squared, and this is a circle of radius z. So basically the cone is composed of circles. At each z, there is a circle of radius z. This is how the cone is made out of circles. Okay, so now we need a parameterization. We're dealing with circular regions again, and all the time when we have circular regions, we think of the polar coordinates. So I would say r of r theta is, so for x, I would choose r cosine theta, for y, r sine theta, but then if you substitute these into x squared plus y squared with the root, you will get r. So the r represents the z, and the theta values are between 0 and 2 pi, because you're having full circles. The r, in the end, the r represents the z values, which are between 0 and 5. So in this example, if we look at this as the theta axis, this is the r axis, the theta is between 0 and 2 pi, the r is between 0 and 5. So again, this is my domain. This is my domain, and this domain is mapped, this rectangle is mapped through this parameterization to get this cone. Now, what is the best parameterization? We mentioned when we discussed curve parameterizations, we discussed that any curve has infinitely many parameterizations. This is still true for surfaces. So any surface has infinitely many parameterizations. For example, just here, for example, another parameterization of this surface would be, I can say r of uv equals, I can choose x as u, y as v, and then z as u squared plus v squared. This is another parameterization. For us, this is not the best parameterization. In fact, this is the best parameterization. Why? So how can we tell if my parameterization is really the best parameterization? Of course, there is no definition for the best parameterization, but we will see later, for our purpose in surface integrals, if the domain of R, which is the parameterization, is a rectangle, like our example here, then the parameterization, I'm going to say, is perfect. This is the simplest ever parameterization, is when the domain is a rectangle. But for example, if you're writing a parameterization and you discover that the domain of the parameterization is a complicated region, that's not a good parameterization. The reason is, when we do surface integrals, we will need to integrate over these regions. So the easier region, the better parameterization. For example, if we look at this parameterization, if we find the domain of our parameterization, it will be a disk. The disk, of course, is not an ugly domain, but the rectangle is much better and much easier to deal with than the disk. That's why we prefer the rectangle over the disk. Then, just to make things complete, I want to discuss this rectangle. How does my parameterization work with this rectangle? So how does my parameterization, how does it take this rectangle into this cone? I want to look at this. So imagine you have a rectangle and you have the parameterization. I want to see how does this parameterization work. So again, as before, this is theta, this is r, this is from 0 to 2 pi, and this is from 0 to 5. Okay. So if you take horizontal lines from the rectangle, so each line, for each of these lines, let's take a specific line. For example, this one, let's say, it is corresponding, let's say, to r equals 3. But for this, the theta is still ranging between 0 to 2 pi. So if we take the image of that line, so r is a 3, but the theta is a variable. So if you go back to the parameterization and you replace r by 3, so 3 cosine theta, 3 sine theta, and a 3, this is what you get from the parameterization. Now, what is this exactly? If you look at the x, y coordinates and you square them, so x squared plus y squared is 9, that means this is a circle of radius 3. But at the same time, the z is equal to 3, this is the height. So basically, this line is mapped into a circle of radius 3 at height 3. So how do we understand this parameterization? Then each of these horizontal lines is mapped into a circle of radius r at height r. This is how the cone is composed out of these circles. So to produce the cone from the rectangle, you take these horizontal lines, you bend them to get circles, you put these circles above each other to get the cone.